Uh, Good day, everyone. I want to welcome you to another statistical machine learning class, and welcome to the month of November. Today, the focus is going to be on inference in Bayesian network, part 2. Of course, the other time I introduced you to Bayesian network. I want to use this opportunity to appreciate those who visited my office hour yesterday. And some of you asked about um, a clue on isomap. You know, I needed to check the announcement section today. I'm going to put a clue on that. And I thought my TA had been posting lab materials. I think somebody called my attention to that this morning among you, that lab materials have not been posted. So I apologize for that on behalf of my TA. So I think I'm going to do that myself today. I'm going to upload lab materials. We got a lot to do today, and I need you to pay attention. There's going to be a lot of algebraic work and how we do inference in Bayesian network. We actually do that in R. So I need you to pay attention. So once again, I want to welcome you to Inference in Bayesian network, part 2. Of course, in the outline, I'm going to walk you through some computational examples. We're going to talk about statistical inference in Bayesian network and how do we implement Bayesian network in R. I want you to take a look at this. Bayesian network is one of the type of probabilistic graphical model. Okay, Bayesian network is directed acyclic. What do I mean by acyclic? There's no cycle, which means the moment it starts from a node, you can't come back to the node. Okay, so that is what we mean by acyclic. Okay, and of course, you know, Bayesian network very useful in factorizing the joint probability distribution using conditional distribution. Of course, using conditional distribution, we're going to save a lot of parameter space. I needed to pay attention and look at the board, look at the variables. We got like, how many variables? That look like, is it 8 or 9? Okay, 8. You got 8 variables on the board. And these 8 variables, of course, there is this interrelationship between them, and that very relationship can actually be seen to be probabilistic relationship. Now, let me tell you this. If each of these variables has 2 states, receptor A, 2 states, receptor B, 2 states, and so on like that, each of them, gene A, gene G, all of them, if they have 2 states, okay, if I want to figure out the probability distribution of the joint occurrence of all of them, is the numbers of parameters I'm actually going to have will be 2 raised to power 8 minus 1. Does that make sense? And 2 raised to power 8 minus 1 is going to be a lot. But if we understand the knowledge, like if we have a prior knowledge or an expert knowledge of how the relationship is going to be, and we have a network like this, I'm actually going to take a look at this. Okay, the number of representation is actually going to be 18 instead of 2 raised to power 18 minus 1. How do I get 18? I needed to pay attention now. Okay, here, number of parameter is going to be 1. It's going to be 1 here. Don't forget I said each of them has two levels, right? So if they have 2 levels, if I know one level, I can use the complement law of complement to figure out the other one. So 1, 1. But if you take a look at this guy, is depending on this. So this is going to be true because I can look at climate C. What is the probability of climate C given receptor A? I can also look at it. The probability of climate C given receptor A complement. Does that make sense? And that's why you're going to have 2. Okay. Right here is going to be 2. Right here is going to be 2. But right here is going to be 4. Okay. You know that guy? This guy here is depending on 2 things, right? You can see it came from, it's like it's having 2 parents. Okay. And that's going to be 4. Okay. And this guy going to be 2. Okay. And this guy also going to be 4. You can see 1, 1, 2, 2, 2, 2, 4, 4. So that was how you actually have this guy here. Okay, 18. Instead of 2 raised to power 8 minus 1. I told you we're going to subtract 1 because that 1 means they must all sum to 1. You know, the numbers of independent pieces of information. So take a look at that. Okay, and that is why we favor a probabilistic graphical model. We favor probabilistic graphical model because when we incorporate domain knowledge, that will allow us to, to see the dependencies. Okay, using what I call conditional independent, we'll be able to save a lot of cost. But you know what? I want it to be focused now. I want to walk us through computation. And I'm seeing a lot of midterm 2 here. On Saturday, tomorrow, I'm going to post midterm 2 practice questions, just like the same way that I did. Now, I need to take a look at this structure. Look at the arrow. Okay? Hey, you can see C come from A, right? Can you see the arrow? C come from A, right? And B come from A as well. B and C come from A. D come from B. Do you see that network? Please interpret the arrow. But you know what? They gave you the conditional probability for C, which is, don't forget, if I want to give a conditional probability for C, okay, because C is depending on A, we're going to have 2. Why? We're going to have, that's why you see probability of C given A, and that very A as to nature could be true or false. Take a look at that. So what are they trying to say? So I just needed to pay attention now. What I'm going to be using now, when I say true, okay, false is going to be a complement. That's what I mean. So which means here is going to be the probability of C giving a complement is 0.3. The probability of C giving A is 0.8. Does that make sense? And of course, you see A here doesn't depend on anything, right? A doesn't depend on anything, right? That's why it's actually going to have a prior. We're going to have P of A equal to 0.4. Then we can also know P of A complement, right? P of A complement will be 1 minus 0.4, in case you want to figure it out. Now, we have for all of that. Now, I need you to pay attention, okay? And somebody asks, based on this structure here, please pay attention. Somebody asks, based on this structure here, okay, what is the probability? Is he writing? Oh, he's not writing on that. Well, it's writing. Okay, I'm going to do this. Give me 1 second. Okay, that's not going to work, but I'm going to do this. Maybe I should come here. Okay, so what is the probability of, what is the probability? Can you see what I'm writing, right? The probability of B, okay, given A complement, okay, So it's going to be this guy, right? That is 0.3. Does that make sense? Force, a force. That's what it means. Now, what if they ask you to find this? What is the probability of B complement, okay, given A? Okay, the probability of B complement given A. And I need you to pay attention. Here you need the knowledge. You need your residual knowledge. What you've done before. Do you know that if I want to use the law of complement, the probability of a B complement equal 1 minus probability of B, right? If I want to condition that on A, this is going to be the same as 1 minus probability of B given A. Look at that. How do I know that? I know that from here. I know that probability of B complement, the probability of B complement equal 1 minus probability of B. Now, if I want to use this particular law now, then if I want them to condition on an event, that was why I can say, oh, probability of B complement conditioning on A equal 1 minus probability of B conditioning on A. Now, if I want to figure this guy out now, if I want to figure that guy out now, that is going to be what? So give me 1 second. The probability of that, say, given A, okay. Now in the network, that is going to be 1 minus, what is the probability of B given A? Do you see that? The probability of B given A is 0.8. That is when it is true, when A is true, okay? What is 1 minus 0.8? So what is the answer? That should be 0.2, right? And that was how the answer here is going to be 0.2. You see that? The probability of B complement given A is going to be 0.2. Now, what of in a situation now, maybe they ask you to find this guy, the probability of B complement giving A complement. Please pay attention. If you don't understand, ask question. Okay. Now, can somebody tell me? That would be what? What formula for extra credit? If I want to find probability of B complement giving A complement, what is it going to be? Go ahead. Exactly. Send me a message for extra credit. That is it. It's going to be 1 minus the probability of B, okay, giving A complement. Now, what do you see? They're going to be conditioned on the same thing. They are when this one is conditioning on A complement, the other one also going to be conditioning on A complement. The only thing that is going to be different is, what you see, the B complement and the B here. Take a look at that. So now that is going to be 1 minus. So what is probability of B giving A complement? Another person? What is the probability of B based on what you see on the board? What is the probability of B giving A complement? Who can tell me? It's 0.3, right? Okay, so that would be 1 minus 0.3. Okay. So what is 1 minus 0.3? That would be 0.7, right? So take a look at that. So I got 0.7 for that. Okay. Now I'm going to go to another question. I'm still using this. Now somebody asks you now, you actually want to find the probability. Somebody said, find the probability of C. Please pay attention. I want to find the probability of C. Okay. Now, if you take a look at C, where is C? Where is C coming from? Where is C coming from? Look at the arrow. Where's C coming from? A, right? Do you see the arrow? C is coming from A. Now, if I want to find probability of C, because C is coming from A, I'm actually going to have the probability of A, comma, C, okay, plus probability of A complement, comma C. Does that make sense? That is what we call total probability. I want to find probability of C. If I want to find probability of C, it's actually going to be probability of A, comma C, or complement of A, comma C. Does that make sense? That's what we call total probability. We actually going to apply your statistical residual knowledge of Bayes theorem, total probability in Bayesian network. Now, what we want to do now? Take a look at that. I want to, A comma C means A intersection C, the probability of the join of A and C. Now, this is going to be written as probability of C given A. Don't forget, C comes from A, right? Multiply by probability of A. That is the first one, right? Then I'm going to go to the second one. The second one is actually going to be the probability of C given A complement now, okay, given A complement now, multiply by probability of A complement. You are not seeing this for the first time. You've seen this something like this before. So what are we going to be doing now? We're actually going to be plugging in values, okay? What is the probability of C given A? The probability of C given A is 0.8. I'm going to put it 0.8 here. Multiply. What is the probability of A is given here? That's going to be 0.4, right? Okay, that's super cool, right? Then plus. What is the probability of C given A complement? Okay, C given A complement is going to be 0.3. You're going to put 0.3 here, right? What is the probability of A complement? The probability of A complement will be 1 minus probability of A, right? And that's going to be 0.6, right? Okay, if you do your calculation right, okay, I think this one is 0.32 plus 0.18. That should be like 0.5, if I'm not mistaken. That should be like 0.5. So at the end of the day, this is 0.32, right? Plus 0.18, and that will give you 0.5. Okay, that's how to figure it out. Now, another one, what if in a situation where we actually want to find the probability of BC. Okay, now I'm going to clean this now. Okay, now another question. You want to find, let me come here. You want to find probability of BC. They wanted to find the probability of BC, right? Let's go back to the structure. Okay, if you want to find probability of B and C, oh my God, look at B and C. There's an A in between them, right? Look at that. B, you want to find probability of BC, but what is in between them? A, right? Because A is in between them. If I want to find probability of BC, I'm also going to use a total probability. I'm going to consider BC when I observe A, or BC when I don't observe A. So in that situation, I'm actually going to have the probability of BC A, okay, plus probability of BC A complement. Does that make sense? BC A complement. Okay, that's exactly what I'm going to have. Okay, now the next thing I'm actually going to do now, okay, don't forget BC. If you go back to the structure, BC, okay, B depend on A, C also depend on A. So it's going to take me to consider this. if I want to get, for instance, I want to get the probability of BCA. Now, BCA means AB is also, you can also say ABC. I'm going to write the probability of what? In conditional form, looking at the structure. BC depend on, B. So I'm going to write BC, okay, given what? Given A. And when I write BC given A, okay, I have to multiply by probability of A. You see that? Then I'm going to do the same to the other side, to the complement side. So I'm actually going to have the probability of BC, oh my God, giving A complement right now, okay? And that will be multiplied by probability of A complement. Look at that. If you don't understand, please ask question. If you don't understand the way I'm interpreting this now, I need you to ask me question. Okay, take a look at that. We want to find the B and C. B depend on A. Look at the arrow. C also depend on A. Both B and C depend on A. And that was the reason why we write what is the probability of BC given A? Okay, multiplied by the prior probability A plus BC given A complement, multiplied by the prior probability A complement. Now, you know what I want to do now? Oh my God. I actually want to do something now. I want to find the BC given A. Okay. Now, if I want to find this guy now, take a look at this. I want to evaluate that guy. I also want to evaluate that guy. I want to consider that separately. Okay. And I need you to pay attention. If I want to interpret this guy right now, how is it going to be interpreted? If the probability, if I actually have this BC here is a comma, B comma C, okay? B comma C, okay? B comma C given A. Now, that is actually going to be the same as probability of B given A, okay? Okay? Now, the probability of B given A and probability of C given A and splitting it out. Okay, take a look at that. If B comma C is given A, I can split it into B given A, C given A. Look at that on the board. Okay, you see what I interpreted? B comma C given A can be written as B given A multiplied by C given A. So that can be partitioned into a joint distribution. Now, if I have that guy now, okay, C given A, don't forget here, there's a probability of A, right? We're breaking that here. Now we're going to do the same to the other side. The probability of B, okay, giving A complement, okay, the probability of C, okay, giving A complement, okay, multiply by probability of A complement. Is there any question at this time? Is there anyone who is not getting that? Let me know if you are not getting that. I'm actually going to explain that if you are not getting that. Okay? Is there anyone who's not getting that? Okay. Now, the next thing that I actually want to do right now, okay, I have B given A, C given A, okay, P of A. It's going to be super easy because I can get this B given A is in the graph. B given A is 0.8. You see 0.8? B given A, we can get that from the graph. Then C given A, we can also get this guy. Probability of C given A, okay, also in the graph, 0.8, okay? Then you just plug them in. Then probability of A, then you can also get probability of B given, you can get all of these, okay? If you put all of those values, if you want to know whether you're right, let me see. Your final answer should be 0.31. 0.31. That should be your final answer. 0.31. If you plug in all those values. And that will be the probability of BC. Any question? Any question on that? Okay. I actually want to go into another one. I want to come back here now. And the question this time around, okay, find the probability of D given A. You know, these are probability queries. These are called inference in Bayesian network. We already have a network. We're actually answering a question of probability queries. Now, I want to find the probability of D given A. Of course, D given A in a conditional probability is actually going to be probability of D, comma A, which is probability of the joint, you remember, divided by what? Probability of A. Do you still remember? Okay, we're using that knowledge of conditional probability in network, in Bayesian network. Now, take a look at that now. Now, when you take a look at what I have now, let us look at the structure and look at the D and A. We want to focus on this guy. Oh my God. We want to focus on D and A, but there is something in between them. What is that? B. So which means the numerator here can be partitioned into, we're actually going to have D, B, D, B, comma, A, okay, plus, D, B complement now, right? B complement, okay, then A. Let me write it there. So, okay, it's not, you understand what I'm trying to write, right? Then everything divided by probability of A. You see that? Okay? Because there is B in between them. We're going to consider a situation where B is observed and when B is not observed. When B is observed, it's B. When it's not observed, it's going to be B complement, right? Did you get that, right? Okay. Now, because I need a space, I think I'm going to come here. Let me clean up this guy. Okay, so I want to find the probability of D or given A, right? Now you want to find the probability of D given A according to the question. But when you look at the network, okay, when you look at the network, you can see arrow go from A to B to D. If I'm seeing A as a grandparent and B as the parent, then I want to call and and B as a parent and D as a child. Now I want to look at what is the probability of a child given the grandparents. Now the probability of a child given the grandparent, now I'm now saying we're going to consider a total probability where we observe the immediate parent, where we don't observe the immediate parent, and that's what we're going to have right now. So this guy now, like I said, is going to be probability of D. Okay, you know, this one, the probability of DA, like I said, using the joint conditional probability divided by probability of A. And I said because, you know, you go from A to D, you pass through B. Okay, it's either you have this guy, comma B, okay, comma A, okay, or means plus, or means, okay, B is not going to be observed. Okay, when B is not going to be observed, it's actually going to be called B complement. Okay, so B complement, okay, comma A, okay, and that is going to be divided by probability of A. That's what I have up to this moment. Now, the very first thing, the next thing I'm going to do now, I actually need to figure out what is the probability of DBA. Okay, that's what I'm actually going to do now. Now, if I want to find the probability of DBA, I'm actually going to find the probability, oh my God, the child now, depending on both parents, right? Okay, depending on A, comma B, Okay. And when I have that, then the prior probability will be A comma B. Okay. Don't forget that. It's going to be A comma B. Okay. It's going to be A comma B. Okay. So when you take a look at this, that's the interpretation of this guy. Okay. In conditional form. Oh, let me write my B very well here. Okay. Then I'm going to do the same. Okay. So the complement. So it's going to be probability of that. Okay. D. Okay. If it is not making sense to you, let me know. Okay. If it is not making sense to you. So D bar, okay, multiply by probability of A, okay, comma, B bar, okay, complement, okay, or now divided by probability of A. So take a look at that. Okay, is there any question at this time? If you don't understand it, let me know. Okay, so far so good, right? Everyone, so far so good, right? Okay, so I think I'm still kind of simplifying. Okay, I'm still kind of simplifying. Oh my God. Okay, I need you to take a look at this guy. Okay, and if you take a look at that guy, also take a look at that guy. Can somebody tell me for a credit? The probability of A comma B divided by probability of A. What is that? Extra credit. You see what you see that on the board? What is the probability of A comma B divided by probability of A? Exactly. Probability of what? Giving A. Send me a message for extra credit. That will be probability. So this guy now, okay, is going to give me, okay, the probability of B giving A, okay, the probability of B giving A, okay, and similarly, the other one here is going to give me the probability of B giving of B complement, right? Giving A, right? That's also going to give me that, right? With that, we're not going to have the denominator anymore, right? We're not going to have the denominator anymore. Okay, so I needed to pay attention to that. Okay, so I'm going to have B giving A and B complement giving A. Now, I need a room right now. Let me just clean this side. Give me 1 second. Okay, I need a room right now. I've told you before, we're gonna be using the knowledge of algebra here. Okay, I need a room right now, and I want to write something right now. Okay, now what this is what I'm gonna write. Okay, now take a look at this. If I have probability of D giving A B, let's come back here. Let's look at the structure. Please focus. I want to rewrite that as something. Probability of D giving A B. Okay, you know, the probability of D giving A B. Now, giving A B, before I get to A, okay, we're looking at the connection between D and A, right? Before we get to A, before first get to B, right? Which means the child is highly more connected to B than to A. Does that make sense? Because B is the parent. A is a grandparent. So because of that, I'm actually going to say we're using the law of conditional independence. Okay, this guy, okay, if you take a look at that guy now, it's the same thing as probability of D, okay, giving B. Let's go back to the network. This is the network, okay? The probability of D giving AB is the same thing as probability of D giving B, okay? That's a conditional independent. So now, if I have that now, and you already know this guy to be probability of B giving A, okay, then it's going to be plus Okay, the same thing here. The probability of D, okay, given B complement, okay, then the probability of B complement given A. Now, all we're just going to do is to start plugging in values. Oh, let me see if I have my final result here. It should be 0.7 at the end of the day if you get it right. If you start plugging in the values, you should get 0.7 at the end of the day. You're going to go to the table. You can find probability of D given B is there, B given that, and all of that. They are there. Okay, I want to move. Right now. I show you this the other time. You can see alarm 1 and alarm 2 depend on burglary in the first one, but the second structure said burglary depend on alarm 1 and 2. The one that make more sense is the first structure. Now, I think I've answered that question yesterday, but it's another question. And the question, they gave you all of these. Consider the second Bayesian network, but this time around, they want you to use this. They want you to use this particular structure, the second structure. Okay, they want you to use the second structure now. Okay, in answering the question, this question here. This question here. Consider the second Bayesian network, assuming the probability of alarm 1 is 0.1, probability of alarm 2 is 0.2, probability of burglary given alarm 1, alarm 2 is 0.8, probability of burglary given alarm 1. Now, this sign here, I'm referring to alarm 2 complement. Does that make sense? And they give you all of that. But look at the question. Look at what they want you to find. Find the probability of alarm 2 given burglary, alarm 1. That's what we want to find. The probability of alarm 2 given burglary, alarm 1. How am I going to do that? I'm actually going to interpret that as this. Look at that. The probability of alarm 2 given burglary, alarm 1 is going to be equal to the probability of the joint of all of them. What is the joint of all of them? Alarm 1, alarm 2, burglary. You know, you're combining all of that. You remember the probability of A given BC is going to be equal to probability of ABC divided by probability of BC. And that was why you see divided by probability of burglary alarm 1. Now, what I'm going to do first, I need to first figure out this guy. What is the probability of the joint? Please pay attention. If I want to find the probability of the joint first, I will have to go back to the structure, the way the structure is written, to get the probability of the joint. Now, if I want to get the probability of the joint, you know what I'm going to do? Probability of alarm 1 times alarm 2 multiplied by burglary given alarm 1, alarm 2. Do you see the structure? Okay. It's going to be equal. I'm using the second structure. If I want to get the probability of the joint, looking at, if you take a look at the structure, it's going to be probability of alarm 1 times probability of alarm 2 times probability of burglary given alarm 1, alarm 2. Does that make sense? And that is what you actually going to have. Give me 1 second. You're going to see now. Don't go there. Don't go there. It's right here. Okay. Now, right here. Can you see this? Can you see that? Probability of alarm 1 times alarm 2 times burglary given alarm 1, alarm 2. What did I use? I used the structure to get the joint of all of them. Put the values, I got that. After getting that now, the next thing that I want to get, so if I've gotten this guy, the next in the line is to get this guy. I want to get the probability of burglary given alarm 1. Now, look at that. Burglary given alarm 1 is going to be a total probability, which is going to be equal to Probability of burglary alarm 1, alarm 2, plus probability of burglary alarm 1, complement of alarm 2. Now, which is what you're going to see here. Okay, which is what I'm finding. Look at this. That's what I'm saying here. Probability of burglary, comma, alarm 1 is going to be probability of alarm 1, alarm 2 burglary. Then in the other one, alarm 2 complement burglary. They're just going to plug that in. Now, the moment you plug that in, okay, the moment you plug that in, of course, if you take a look at this, you can find that. And at the end of the day, that was what I put together to be able to get what I got here. Using the result that I got here, 0.016, and the 1.072 that I got here. And that was what I used. Okay. Now I quickly want to move how, for instance, the one we've done for now is when you have a network. But what if in a situation where you have given data set, you're giving data set, okay? And when you are giving data set, how do we build the network? We call that a 3-step process to curate and learn the network structure. We're going to start with input training data. We're going to learn the structure. After learning the structure, we can learn the structure from data, but that will be complicated. And we can learn the structure from the experts. Okay. Then we have a parameter learning. Then we draw inference. There's a particular method that we use in learning the structure. Okay. Learning the structure, we can use e-climbing. You know what they call e-climbing? When you iteratively construct different kind of structures, and you are, what you are trying to do is you delete, you adjust based on some score value. Maybe you're using VIC, you generate different kind of structures like this. Take a look at that. Okay, you started with nothing, you start with this one, you do this one, you start revising them until you get. So in situation where you don't have a domain knowledge, we draw different kind of structures to represent the data, okay, and we use some module or structure selection criteria to arrive at that. And you know what? I'm going to show you something now. We make inference after learning the structure. The inference could be exact, it could be approximate. But I quickly want to show you to working with, I want to show you a real life data. Imagine a group in this class working on Bayesian network, and you have a real data set. Pay attention now, okay? Take a look at this. Let's say you're working with this data set. These are the features. Male, you have information about age, education, okay? Whether the person is a smoker or not, okay? Number of cigarettes. You have all of this in your data, and you don't know what the structure is going to be. Maybe the expert doesn't really know the interrelationship among them, and you want to figure it out yourself using R. Now, this is a structure that will come up at the end of the day using a code in R. Okay. Now, but let me tell you this: when you have so many features, okay, what we do in the modern day world, we can use lasso regression to remove some insignificant features, because the otherwise your network will be complicated. And that's why I've seen an article on Bayesian network with lasso. And what they use lasso to do is to reduce the dimensionality before they fit the network structure. Okay. Now, based on the network structure, you may want to, based on what you draw now, you want to answer a question on what is the probability of a diabetic person having a chronic heart disease? Okay, it's 33% as compared to, so you want to figure out how do I get the 33% and the 15%? Okay, I'm using the structure now to answer the question. Look at that. That's an R code. Okay, you see here. You see 33% here, and you see 15% here. That's we're interpreting that. Okay. This is another inference question. Another inference question. But how do you get a structure in R? You need to load a package. Look at the word. Set seed, load all of the packages. Okay. Now, when you load, when you have that, okay, you can write A, B, C, D, E, F, depending on the numbers of features. If I write, for instance, based on this now, I'm just assuming, based on this guy now, okay, if I write, if I do arc into DAG and this, and maybe somebody already told me I have a domain knowledge, okay. Now, if I want Aru to draw this, you know what I'm trying to tell Aru? I'm trying to tell Aru that, okay, A is a parent, C is a parent, but B depend on A, D depend on C, F depend on that. Draw that for me. When I do plot DAG in R, it's going to automatically give me that. And we can also learn the structure directly. But let me tell you this, learning the structure directly from data may be complicated. And that is the reason that informed my decision of putting you in group. Because in a research world, nobody, I came to realize something in the world. Even though we are fine on our own, but we need one another. Particularly in a research world, we collaborate. If I want to work in this area, instead of me to worry myself about how I'm actually going to learn the structure from the data that may be too complicated, I can actually collaborate with somebody in that particular field that have the background knowledge of what the relationship is going to be. This is where I'm going to stop today. Like I said, I'm actually going to post all lab materials. I'm also going to post something, a clue on how to do isomap as well, for you to be able to, that way the completion of the current assignment. Make sure you all stay safe and have a lovely weekend. Bye for now, everyone.